Hi, welcome to our next level 3 differentiation video. We look at implicit differentiation in this video. Today, the vast majority of functions and graphs you've come across are called explicit functions. An explicit function is a function written as y equal to something. And here's some examples you've probably seen before. Now we're going to look at implicit equations, and these are equations that are not written explicitly as y equal to something. And here's some examples below. You've probably seen the two on the right-hand side in your work on level 2 graphs. We're going to quickly define a function as a rule, algebraic rule, that generates only one y value for each x value. So the graph, the parabola on the left, when x is 1, is only one y value. But looking at the circle on the right, when x is 1, there are two y values, one positive and one negative. So the circle is not defined as a function. It's an implicit equation. So example 1, let's differentiate the circle rule, x squared plus y squared equal to 9. It's an implicit equation. It's not a function. All right, let's get into it. The x squared differentiates as normal to 2x. The 9 will differentiate to 0 as normal. Number disappears. Now we've just got this y squared, and this is the tricky bit. You need to think of it like a composite function. So the 2 will come out the front of the y. I want you to pretend the y is inside brackets. We leave y alone and we take 1 off the power of 2. Now we need to times by u dash because it's composite. And u dash is whatever's inside the brackets differentiated. Well, what's inside the brackets is y. And y differentiates to y dash. So let's tidy this up to get 2x plus 2 times y to the power of 1, but we don't write the power of 1, times y dash, which is equal to 0. Right, let's take this plus 2x and subtract it on both sides to put it on the other side. And let's divide both sides by 2y to cancel the 2y, and that leaves us with our y dash, or if you prefer dy dx, which is negative 2x divided by 2y. This is the gradient for our implicit equation above, our circle formula. Right, let's get into example 2. Find the gradient of the graph 2xy squared minus 18 equal to 0 at the point 1, negative 3. Well, here's what the graph looks like, a weird looking graph. Here's the point 1, negative 3, and our job is to find out what is the gradient at that point. Right, let's get into it. Well, this unfortunately is even trickier because this is a product rule. We've got a function times a function. So over here is the working we need. We have 2xy squared, f is 2x and f dash becomes 2. And our g function is y squared. And we showed you in the last example how to differentiate that to get 2y times y dash, or 2y times y dash. All right, so let's go back and use the product rule. So we need to go f, which is 2x, times g dash, which is 2y times y dash, plus f dash, which is 2, times by g, which is y squared. Now let's keep going with the minus 18. A number by itself differentiates to 0. And on the other side, equal to 0, well, 0 differentiates to 0. Right, let's tidy this up to get 4xy times y dash plus 2y squared is 0. Right, let's subtract 2y squared on both sides. And let's divide everything through by 4xy to cancel this here and leave us with y dash, the gradient rule, which is equal to negative 2y squared over 4xy. We can simplify that if we wish. Right, now we're given the point 1, negative 3, so let's substitute. Notice we need an x and a y to get the gradient. Substitute that into y dash to get a gradient of 3 over 2. So having a look at what the graph looks like, at the point 1, negative 3, we've figured out the gradient. It rises 3 and runs 2. Great, thanks for watching.